So, Cubemaps. What are they? Well, they are a special kind of textures that consist not of a single image, but a set of 6 images, each representing a side of an imaginary cube. And why would we want something like this? Well, they provide a different and very handy way of sampling colors. Imagine that you're standing at the very center of a perfectly cubic room, each wall as well as floor and ceiling of which is beautifully painted. And you can turn your gaze to any spot in this room and see some color. And this is basically how Cubemaps work. In technical terms, to sample a color from a Cubemap, you just use a direction vector that points to some color in such an imaginary cube. Now, what are the applications of this? Well, you can actually get pretty creative, because they basically give you a representation of some kind of enclosed environment. The textbook example is of course the skybox technique. Like, you have 6 perfectly fitting together pictures of some faraway environment, and you just draw them as a backdrop behind your actual game world, right? Also, for example, you could sample ambient light from a downscaled skybox and get a nice scattered light that fits very well into the environment. Or you could, for example, render your scene into a cube map from some specific position and then sample from that cube map in the shader using the surface normals as texture coordinates, and you would basically get reflections for your reflective surfaces. Also, cube maps are used to implement shadows that are coming from the point light, since such a light is emitting in all the directions. In this case, we would only draw depth information into a cube map. And we will get to this in future when we'll be implementing shadows. And yeah, there are even more interesting applications, like for example those fake interiors that you can see through windows in some games like the Spider-Man, for example. But as usual, let's start with the basics. Let's just create a cube map texture and then draw an actual cube textured with this cube map. So, to create such a texture, we need to upload 6 square images of the same size. So let's find some example assets first. The easiest cube map asset that we can find online is, of course, skybox images. So maybe let's use one of those. And they can actually come in different formats. The most straightforward way is just 6 files with 6 different square images that we can load one by one. Sometimes they can be just a single image laid out in a specific way, which we can also quite easily load. And I think we'll do it later just to illustrate how to do it with the SDL GPU API. And finally, they could also be not in the cubemap format, but rather in this single panorama image in the equirectangular projection, like this, right? And for those, we could use an inline tool, like this one, for example, to convert them into cube sites. And by the way, this is a pretty popular site, Polyhaven, that provides textures and models, and also something called HDRIs, right? And this stands for High Dynamic Range Images, I think. But HDR is something that we'll talk about in future, because that's also a really interesting topic, and it's a natural continuation of the lighting topic. But this site actually also provides an option to download a tone-mapped low dynamic range variant of their images. So you could also use those as well. And you see this tool can actually generate cube map faces out of this panoramic image. Anyway, there's this pack from itch.io, which is just a bunch of generated skies that somewhat fit the cartoonish visuals that we have so far. And moreover, this pack conveniently has both separate images as well as the single image, so we can experiment with both. So let's place them in our texture folder, maybe in a subfolder like skybox. So here they are, and let's see what do we need to do in the code. In the end, we will need the texture, so let's maybe go bottom up and start from the GPU uploading. So let's take a look at our upload texture function here. It creates a texture with the default type of 2D. So let's maybe make it explicit, like this. Type is D2. And if we take a look, that D2 is the default 2D texture, right? And there's also a cube, which is exactly the cube map that we are gonna use. Anyway, next it creates a transfer buffer, copies the pixel data into it, and calls the upload to GPU texture function. So for the cube map, we'll do it similarly, but instead we'll pass 6 slices of bytes create a cube texture with 6 layers and perform 6 uploads. So let's copy this procedure, rename it to something like upload cubemap texture. Actually, let's call it upload cubemap texture sites maybe. It might be a bit of an ugly name, but we'll have another variant that uploads it from a single image later, and we want clear names. Now, for the arguments, instead of a single byte slice, we'll take a fixed array of 6 slices. And actually we can even take advantage of Odin's enumerated array feature and use SDL GPU Cubemap face to index our array. Like this. Now, instead of width and height, since it's a cube, we only need a single size value, so let's have that instead, like this. For texture creation, we'll use the cube type. Format and usage are the same. We want a standard 8-bit RGB in the sRGB space, and we just want to sample the texture in our shaders. For both width and height, we'll use the same size value. And this layer count or depth, in this case, is the number of cube size, so 6. And we still don't care about mip mapping, so we leave num levels as 1. Next, we need a buffer that holds the pixels for all the sides. And we can calculate its size in 2 ways. We can either calculate it using the given size, knowing that we have 4 bytes per pixel, or we can just sum the length of all pixel byte slices and get the total size. And this might be a good place to do a sanity check, so I'd say let's calculate the size in bytes for one side and check if all the pixel slices we receive are of that size. Something like this, we just iterate over all the side pixels and assert that their length is what we expect. Next, we change the size of the transfer buffer to side byte size multiplied by 6, so it can fit all the 6 sides, like this. Next, we want to copy side pixels into the transfer memory one after another, so let's just introduce some offset variable, iterate over our pixel data, and copy the memory using the offset, and increase the offset by the side size every time. Now, to use this nice slice syntax to offset a destination pointer, we need to transmute the transfer memory here into Odin's multi-pointer of bytes, just like we do in the upload mesh procedure here, right? So let's do that, just like this. And finally, we need to iterate once again and add the upload commands for each side. We need to specify the texture buffer offsets to the upload commands, so let's reuse the variable, let's set it to 0, add the for loop, and note that we use both the value and the index in the iteration. And remember that the index is the GPU cubemap face, which is something that we will need to pass to the upload command as a layer number. And remember, the second argument to the upload to GPU texture procedure is this texture transfer info that specifies the transfer buffer, and we will also need to specify the offset, because each side will have its own offset in the memory. So we simply specify the offset as U32. And then for the destination, in addition to the texture, we need to specify the layer, and the layer is the cubemap site that I just mentioned. And we also need to cast it to U32, like this. And finally, both for width and height, we use our size value. And of course, do not forget to increase the offset by the side byte size. Now we want to load the images from disk and pass them to this procedure. So let's go into our asset Odin file and look at our load pixel procedure. So here it is. It loads the file using the stb image library and calls upload texture. For Cubemaps, we want to load 6 files and call our new upload cubemap texture sites procedure, right? So let's extract the file loading stuff into a separate procedure like load pixels or something. It doesn't need the copy pass because it doesn't upload any textures, but it needs the texture file argument, like this. And that needs to return the pixel byte slice as well as the image size. Let's make it return a pair of U32s because that's what SDL API expects. Now we just move all the stuff into load pixels, as well as the slice creation. Let's rename these pixels to pixel data or something. Fix the assert. So the pixels return value will be our slice constructed from the pointer. And we already have the image size local variable, so maybe let's rename the return variable to just size or something. And assign it to the image size casted to U32. And we need to add the return for the multiple return function. Now back in the load texture, let's call our load pixels, pass the resulting slice to the upload texture, and we don't need to cast the image size to U32 anymore because it's already that. Now this is wrong, this needs to be pixel data. And let's also extract this STBI image free call into a free pixels procedure. And to get the raw pointer to the data, we call the raw data function. Now add the free pixels call here. And now we can reuse the load pixels to load the cube map faces. So let's add a new procedure to load the cube map from 6 files, and let's also use the fixed array similarly to what do we do here with the pixels, right? Because that will give us a very readable syntax later on. So let's call it something like load cube map texture files or something. That takes the copy pass as well, and the fixed array of texture files. Actual enumerated array using the SDL GPU cube map face as an index. And that would return the same GPU texture. So for that we need to create a fixed array of byte slices, so we can pass it to the upload function, and we can simply fill it in a loop. Now this is where it would be nice to actually do a check if the images are of the same size. So let's do it like that. Let's create a size variable, and then in the loop, if the size is 0, we set the size to the size of the first image. Otherwise we just assert if the image size x is equal to the previously set size. And we should probably also assert that image size x equals image size y, because it should be a square. Now we call our upload function, pass the copy pass the pixels and the size. Finally we should free all the pixels and return the texture. And yes, the return type should be of course a pointer to a texture. So that should be it. Let's try using it and load the actual cube map texture. So let's call our function here in game init. And we need to pass the files here. And if we take a look at this cube map face enum, you see that there are these values, right? And we can just copy them and use them as a kind of name indices in our fixed array. Basically like this. Let's add a folder prefix and the extension. Now let's see. So positive x is the right texture. The negative is left. Positive y is up, or rather top. Negative y is bottom. So positive z, I think it's the front because it's facing the forward vector. Although I might be mistaken, so we might have to change this later. And the negative is back. Let's see if that compiles and doesn't crash. Seems to work so far. No error messages, so that looks good. Now, how do we draw a cube textured with a cube map? First, we need a cube mesh, and to draw it we need a new graphics pipeline that uses the shaders that do the cube map texture sampling. So let's maybe start with the shader, and we'll make a simple unlit one. So let's just copy the light shape as a kind of template and take a look at what we are gonna change there. So here I named them cube map. Let's start with the vertex shader. So we will need the view projection matrix and we will need the model matrix so we can draw the cube at some position. Then we need the vertex position. We need of course to output the clip space position. So this is a good start. The next thing that the vertex shader needs to output is a texture coordinate. However, as we discussed before, the texture coordinates for cube maps are direction vectors and not just a pair of 2D coordinates. So the texture coordinates would be a float 3. Now, how to calculate these texture coordinates? Well, we actually don't need to calculate them, because the input position is of course the position of the vertex. And if our cube mesh has its vertices around the center, then that would be exactly the required direction vector. And as far as I understand, it doesn't even need to be normalized. Any vector that can be treated as a direction should be fine for the Cubemap texture sampling. So let's simply output input position as output texture coordinates. Something like this. Now let's go to the fragment shader. Let's see, we actually don't need any of the global information, so we can remove this block. Then we of course need to pass our texture coordinates from the vertex shader. This out radiance doesn't make any sense, let's remove this. Now we need a texture and sampler to sample our Cubemap texture, right? And they are defined exactly as we do with our entity shader, except that we use texture cube instead of texture 2D, right? And we use the same binding numbers and the space tool for the fragment shader. Now in the main function we simply sample the Cubemap given our sampler and return the result. So as you can see, that's very similar to the normal texture sampling, except that we are using the float 3 direction vector as a texture coordinate. Now let's go back to our game. Let's go to our game state structure and add some new state. So what do we need? We need a mesh. Let's call it test Cubemap mesh or something. We need a texture that we just loaded. Let's call it test Cubemap texture. And we need a new pipeline. Test Cubemap pipeline. Good enough. Let's go back to game init. Let's change the Cubemap local variable to the global state assignment. Let's also generate the mesh. Let's make it 0.5 meter large. And now we need to set up the pipeline. And this is actually getting a little bit annoying, right? Because we have the normal pipeline that we use for entities, and then we have the light shape pipeline that we use for our light debug draw, and then we are adding the new one, and they all are very similar, right? The only real difference is the shaders, the vertex layout, and that's it actually. So maybe we should start thinking about some kind of abstraction for creating pipelines for different things that we want to draw using different kind of rendering. For now, let's just add a to-do, something like this, unify and abstract pipeline creation. We will get back to it and make it a little bit better. But for now, let's just have another of those functions and set up our new shaders. So I copied the light shape pipeline, named it setup test Cubemap pipeline. Let's change the shader to Cubemap. Now the vertex attribute seems to be fitting because we only need the position, and this is what we defined here. And everything else should be fine as is actually. Let's of course assign it to the new field. Back in game init, let's call it. Now it should be ready for rendering, so let's go to the game render and do some drawing. So the drawing is actually really similar to how we draw the light shape, so let's copy paste that and change stuff here. So the pipeline is of course our test Cubemap pipeline. The translation is some position. Let's use maybe something like this, right? A little bit to the left, a bit above the ground, and a bit to the back. Then we change the mesh bindings to our Cubemap mesh. And of course we need to bin the texture sampler. Like this, and that should work. And as you can see, we have quite a lot of very similar copy-pasty code here, right? We do this for the lighting, then we do this for this test Cubemap, and then we do almost the same for entities, which means that there is a pattern here. And indeed there is, these are just different objects with different materials, and we need a better notion of the material that includes the shader and the pipeline and all the data binding. So this is something to think about. However, this is a really difficult thing to actually come up with a good design for, because we really need to balance between simplicity, flexibility, and performance with regard to batching and whatnot. So this is something for the future. For now, let's keep it like this, and maybe we will do a slight cleanup a bit later. So let's see if that works. So here's the game. Now the cube should be somewhere on the left, and yes, here it is. And you can see it's very pretty. It's textured with a single texture using the Cubemap directional sampling. And it looks like I didn't even mess up the forward and back faces, so that's nice. So that's some progress. Maybe one quick thing that we can do just for fun is go to our Cubemap pipeline and change the cal mode to cal the front faces instead of back. Then put the model a little bit higher, like 0.5, and take a look at it. So it looks like a kind of weird portal into another dimension, right? And if we go inside, it almost looks like a skybox environment, right? It is a little bit distorted, and that is because we are not exactly at the center. I think that's enough for this video. Next time we are gonna try to actually implement a skybox, and I think I will do it in a slightly different way than most of the beginner tutorials, because I learned some cool tricks regarding that. So stay tuned.